Am I wrong, or was my teacher wrong? Due to the white on black, I had to take out a loan to print this one, but I won't let such simple trivialities like bankruptcy stop me. Today, we have a fella who just took the national exam in Sweden, and on the exam, they had this problem concerning the maximum area of this rectangle. Solving the problem involved a parabola and a quadratic expression, some of the things that really frighten students of algebra courses. But in this situation, the student might have got the double whammy of nasty parabolas and quadratic expressions, and a teacher being wrong. But let's take a closer look and see who went wrong and how it might have happened in this problem. We'll have to go back to the post to see exactly what the problem to be solved is, so let's take a look. We start right away with the given information. Essentially, the premise was to prove that the biggest area of the big rectangle, that's this outer rectangle here, was 200 centimeters squared. And we knew that the small rectangles inside the big one were the same size. Furthermore, all of the lengths of all of the segments on the figure are equal to 80 centimeters total. So the conditions are that we have these three equal rectangles brought together to form one big rectangle. We know that the lengths of these white segments add to 80 centimeters. Under these conditions, there are several different big rectangles we could form. It's our objective to prove that the biggest such rectangle has an area of 200 centimeters squared. This is what we would call an optimization problem, since we're trying to maximize the area of the big rectangle. You can of course see the OP detail his solution strategy. I'll go ahead and walk you through what he did myself. Of course, the crux of a problem like this is to find a function for the quantity which is to be maximized. In this case, we're trying to maximize the area of that big rectangle, subject to the constraints. So the idea is to find a function for that area. In this case, it's going to end up looking something like that. And then we need to find this point on that function which maximizes the area. Of course, when the function looks like this, it's clear there's a maximum here. In other situations where a function might look like this, it's perhaps not as obvious that there could be a maximum, but even in that situation, we could be given constraints that might restrict our points of interest to, say, an interval like this, in which case there is still a maximum, it just happens to be at the very end. Regardless though, let's go through the details here, and let's begin with just a quick sketch of the situation. We have this big rectangle, and it's composed of three equally sized smaller rectangles. Following the OP's labeling, he labels this width here x, and this length here he labels y, so that each of these smaller segments would have a length of y over 3. Again, as the OP described, the lengths of all of the segments are to add up to 80 centimeters. We can use this information to write our first equation. If all of the segments add to 80 centimeters, well, using this labeling, we know there are 1, 2, 3, 4 copies of x, and of course 2 copies of y. Thus, we would have that 4x plus 2y is equal to 80. This is one equation in 2 variables, so we can't figure out what x or y equal, but we can still solve for y in terms of x. Let's do that now, subtracting 4x from both sides to get that 2y is equal to 80 minus 4x, and then dividing everything by 2 to solve for y. After doing that, we have y in terms of x. Y must equal 40 minus 2x. Now, we can use this so that the thing we're trying to maximize, the area, is a function of a single variable. What is the area of this big rectangle? Well, of course, it's length times width, or x times y. So we might write that a is equal to x times y. This has 2 variables, which is not super easy to work with, but now we know what y is in terms of x. So we can go ahead and replace y here with what it equals in terms of x. Thus, we have x times y, which is 40 minus 2x. From here, of course, we see the quadratic expression materialize, distributing the x through the parentheses. This is equal to 40x minus 2x squared. At this point, we are pretty close to a solution. We see that we have a formula for the area, and it's a quadratic expression with a negative in front of the x squared term. This means that if we graph the function for area, it would be a downwards facing parabola. Then, if we want to find that maximum area, well, that occurs at what's called the vertex of a parabola. So we just need to use the familiar formula for the vertex of a parabola. The notation I'm familiar with in America for that would be that x is equal to negative b over 2a. This is the x-coordinate of the vertex of a parabola. In our case, b is 40 and a is negative 2. We could plug those numbers in here to get the x-coordinate of that maximum, and then we could plug that into the area formula to find that the area should be 200 centimeters squared. That would solve the problem of showing the maximum area is 200 centimeters squared. However, this is not quite what the OP did. He used something a little bit more specific to Sweden. One thing to know about parabolas is that they are symmetric about what's called, of course, the axis of symmetry, which is a vertical line passing through the vertex. You can see how the parabola looks the same on this side to the left of the axis of symmetry as it does on this side to the right of the axis of symmetry. So if, for example, we know the two roots of the parabola, we know that those are like mirror images of each other across the axis of symmetry. And so we could just find what's halfway between them in order to locate the vertex of the parabola, if, for example, we didn't just straight up know the formula to do that. Now, to find the roots of a parabola, or the solutions, or the zeros, there are a lot of words for these things where it intersects the x-axis, we would typically use the quadratic formula. Apparently, though, in Sweden, they use something called the PQ formula, which is really the exact same thing, but it does look a little bit different. The OP uses this formula, taking 40x minus 2x squared and setting it equal to 0, just like we normally would if we're trying to find the zeros of a quadratic. After setting it to 0, he divides both sides by negative 2 so that this coefficient in front of x squared is a 1. Then the expression on the left is x squared minus 20x equals 0. Again, we've just divided everything by negative 2. This is now in the PQ form that they teach in Sweden of x squared plus px plus q equals 0, and so now we can apply the PQ formula. You can see that in our case, p is negative 20, and q, the constant term, happens to be 0. We don't have a constant term. Now, the PQ formula is as follows. It is, of course, a formula for the solutions to the equation, of which there are two, x1 and x2, and this is equal to negative p over 2 plus or minus the square root of p over 2 squared minus q. So this is just the familiar quadratic formula, negative b plus or minus the square root of b squared minus 4acl over 2a, except with a forced to equal 1, and the terms in the numerator, the negative b, which in this case is negative p, and then the square root part, have been written separately. You see the division by 2 here. The division by 2 with the square root has just been taken into the square root. Since we take a division by 2 into the square root, now it's actually acting as division by 4, which is why you see this over 2 squared, and where you would expect for AC, that 4 has actually been divided out, and of course A is 1, so all that's left is C, which again in the PQ form appears as Q. And once it's in this PQ form, you can see that plus or minus that's emblematic of the symmetry of a parabola. In fact, it's this part of the PQ formula which tells us where the vertex is. If we go forward some distance, we get a root, and if we go back that same distance, we get the other root. That plus or minus is what creates that symmetry. So it's this part that stands alone without the plus or minus that is the x position of the vertex. That, of course, is what the OP uses to locate it, negative p over 2, to find the line of symmetry where the vertex lies. So we're looking at that vertical line where x is equal to negative p over 2, which in our case is negative 20 over 2. So negative 20 over 2, the negatives cancel out, and 20 over 2 is 10, so this is positive 10. That means the maximum area for our big rectangle should occur when x is equal to 10. So we go back to the area formula, which was 40x minus 2x squared. We don't want to use xy because then we'd have to separately figure out what y is. Let's just use this expression that's all in terms of x. And we're going to plug x equals 10 into that expression. So it appears the maximum area should be 40 times 10 minus 2 times 10 squared. Sure enough, this is equal to 400 minus 2 times 100, which is minus 200, and so the maximum area is 200, if you want to put in the units, centimeters squared. This was the student's solution, which seems to have accurately solved the problem, since, as he describes, the problem was to show that the big rectangle's maximum area was 200 centimeters squared. So then where's the drama? Well, of course, as the OP says, my teacher said I was wrong. The answer was something with 4 and some decimals, but she did give me a point for getting the formula correct, that a equals x times 40 minus 2x. But of course, the question is, was my answer incorrect? The OP says no matter how much I check, the answer is always 10. I'm not sure what that means here because the answer seems to be a valid solution demonstrating that the maximum area of the big rectangle is 200 centimeters squared. As the OP presents it, the problem was not to find the horizontal position of the vertex. The answer to that was x equals 10, at least we think. But I guess if they're saying the answer is 10, that must mean that when the teacher says the answer was something with 4 and some decimals, the teacher's claiming that the proper x-coordinate should have been 4 point something or other. The OP also goes on to say that because of missing points on this question, they actually got a C instead of a B on this standard exam, so that's certainly a shame. Now, from the process they described, everything, as we could see, was totally correct. If you haven't seen the PQ formula before, that looked a little weird, but it's just the quadratic formula written slightly differently, so nothing here is invalid. That doesn't leave us with many options for how the teacher could be getting 4 point something or other, except unless the problem is not actually what the OP described. And if you stop to look at these words closely, that might have occurred to you several minutes ago. The OP says something pretty strange here when describing the problem. All of the lengths of all the segments on the figure were required to equal 80 centimeters, basically saying the perimeter is 80 centimeters. That's kind of a concerning phrase because saying all of the segments add up to 80 centimeters, that's very specific. You know, what that means is that add up the lengths of these segments and you get 80 centimeters. But then he goes on to say, so basically the perimeter is 80 centimeters. But that's a far more ambiguous statement. The perimeter of what? Of course, the problem is concerned with the area of the big rectangle, so maybe it's the perimeter of the big rectangle, but that doesn't count these two segments, which in the OP's solution were counted. Alternatively, there's also the perimeter of the 3 smaller rectangles. That's another possibility. Those perimeters, if we added them up, would count these segments twice, since each of these segments is part of the perimeter of 2 rectangles. So maybe the original problem is not what the OP solved. The OP solved some variation, and if we look at some other possibilities for what the problem might have been, we'll see that 4 point something or other that the teacher mentioned. Before we do that, maybe it's worth checking what y was in our original solution to make sure that wasn't 4 point something. The way we solved it got x equals 10, so y would be 40 minus 20, which is 20. All right, so that's not 4 point something. And if we look at y over 3, the length of one of these individual segments, that would be 20 over 3, which is 6.6 repeating. So no 4 point anything there. All right, so considering different possibilities, the first way the problem could have been intended is that the lengths of all the segments added together is 80 centimeters. That's what the OP said the problem was, and that's what we already solved. So in that problem, we counted all of the highlighted segments. Perhaps the most obvious alternative possibility is that the perimeter being 80 centimeters meant the perimeter of the big rectangle is 80 centimeters, and thus we wouldn't count these two interior segments that aren't really part of that big rectangle shape. In that case, our formula for the perimeter would not be 4x plus 2y equals 80, but rather 2x plus 2y equals 80, or dividing everything by 2, x plus y equals 40. From there, we would have, of course, that y equals 40 minus x. So then again, we could try to maximize the area. The area is equal to x times y. In this case, y is 40 minus x, so the area is equal to 40x minus x squared. We could use the good old-fashioned American way of finding the vertex, which must lie at a horizontal position of negative b, which in this case is negative 40, over 2a, which in this case is negative 2. This ends up giving us an x value of 20, and just as in the previous solution, this would give us y equals 20 as well. So still no 4 point anything. And if we plug this into the area formula, this would give us a max area of 400 centimeters squared, not what it was supposed to be, which was 200 centimeters squared. So that can't be the intended solution either, leaving us to consider perhaps the most exotic possibility, which is that the perimeter of 80 centimeters was supposed to apply to the perimeter sum of these three smaller rectangles, which means that these segments should be counted once, these segments should be counted once, and the two interior segments should be counted twice. That would lead to the equation 1, 2, 3, 4, 5, 6x plus 2y is equal to 80. Dividing everything by 2 gives us 3x plus y equals 40, and then finally solving for y, we get y equals 40 minus 3x. Again, we could take this right back to our area formula and crunch the numbers. A equals x times y, and in this case, y is 40 minus 3x. That leads to this quadratic expression, which, using the vertex formula, x equals negative b over 2a, we can locate the vertex. Again, that's where that maximum area occurs, and it must be at a horizontal position of negative 40 over negative 6. And this gives us that familiar number of 6.6 repeating. So again, not 4 point anything. And once again, if we plug this in to solve for y, y will be equal to 20. And again, if we plug this in to find that maximum area, it's a little bit over 133. So again, not 200 centimeters squared as needed. So the student's solution was correct for the problem that they solved, and none of the plausible alternative problems that maybe were actually intended give us the teacher's claimed answer of 4 point anything. And again, the student lost critical points because of this apparent error, bringing their grade from a B down to a C. But here in Sweden, the land of the PQ formula, we actually get the good ending. The OP later replied to somebody who gave their input on the problem. OP thanked them for the input and says that they got their missing points back and their grade was upped presumably to the B that they had anticipated, if not for those points that were erroneously taken away. They then go on to talk a little bit about the PQ formula. And apparently they don't actually learn the quadratic formula, which makes sense since that PQ formula is really the same thing, just requiring that A is equal to 1. I have, as you can see, cut the post off here, link in the description if you want to go read the whole thing. Of course, the problem of optimizing anything, like in this case, finding a maximum area, is something that has a lot of real-world applications. In the case of something that can be modeled by a parabola, it's easy to optimize since a parabola has such beautiful symmetry and an obvious peak or trough at the vertex. But if and when you take a calculus course, you'll learn more sophisticated techniques for optimization involving what's called the derivative, which can be applied on much more exotic functions than the parabola. A couple morals from this story. For one, you can get your points back if you just go talk to your teacher. Of course, you're not guaranteed to get them back. You might actually be in the wrong, or maybe there's some other reason you might not get points back. But if the teacher's actually made a mistake, you have a pretty good shot at getting some points back. And make sure you read problems carefully. There are lots of ways this problem could have been misconstrued. Of course, if this diagram was included, the way that the OP explained the problem as counting up these segment lengths and saying they all add to 80, well, that makes sense, because why else would these segments be present in the picture if they weren't relevant to that perimeter of 80 centimeters? If your interpretation of a problem completely ignores some important features of an attached figure, you might want to double check the problem. In this case, the OP understood it correctly and answered it correctly, and thankfully earned the points they deserved. And for those who wonder, when am I ever going to use this parabola PQ formula stuff? Here's a really simple example. If you want to build a rectangle enclosure and maximize the area with the perimeter that you know you have available to you, easy. Just use the PQ formula. Or more specifically, this one little part of the PQ formula, which tells you the horizontal position of the max or min. Let me know in the comments if you've learned the PQ formula or any other interesting variation of the famous quadratic formula. And be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and untuck the table. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue
Planet faded.
Psych!